Hey guys, so this is a continuation of the previous recording where we had analyzed the unbiasedness of our generalized estimator z is equal to lambda 1 times x1 plus lambda 2 times x2. And in this recording, we're going to analyze our generalized estimator for variance, and we're going to find out what condition these weights, that is lambda 1 and lambda 2, what condition these weights must satisfy in order to minimize the variance. So in the previous recording, we already concluded that in order for our generalized estimator to be unbiased, the sum of the weights must equal 1. And now in this recording, we're going to analyze the variance of this generalized estimator, and then we're going to find out what condition these weights must satisfy in order to minimize the variance. Because remember, least or minimum variance means that the estimator is going to be the most efficient. Okay, so let's analyze the variance of our generalized estimator. So sigma squared x is equal to variance of lambda 1 x1 plus lambda 2 x2, and using variance rule 1, this can be rewritten as variance of lambda 1 x1 plus variance of lambda 2 x2 plus 2 times the covariance between lambda 1 x1 and lambda 2 x2. So here we have used variance rule 1. Okay, next what we can do is we notice that the covariance between lambda 1 x1 and lambda 2 x2 is going to equal 0, because we are assuming that x1 and x2 have been generated independently, so they are independent observations. So assuming x1 and x2 are independent observations, their covariance equals 0. Okay, so this third term is going to disappear, and we're left with the first two terms, and we can use variance rule number 2 to rewrite that as lambda 1 squared. So we can just bring out lambda 1 and lambda 2 because they're constants. So lambda 1 squared times the variance of x1 plus lambda 2 squared times the variance of x2. Okay, now as we have already discussed in the previous videos, when we are at the planning stage, we know that the variance of x1 is going to equal the variance of x2, which is going to be the same as sigma squared x. So at planning stage, as a beforehand concept, we know that variance of x1 equals variance of x2, which equals sigma squared x. Okay, so using that idea, we know that we can rewrite variance of x1 and variance of x2 as simply lambda 1 squared times sigma squared x plus lambda 2 squared times variance of sigma squared x. So now sigma squared x is common, so we can simply rewrite this as lambda 1 squared plus lambda 2 squared. Okay, now we are going to continue on the next slide. Okay, so this is what we had. We had sigma squared z is equal to sigma squared x times lambda 1 squared plus lambda 2 squared. Okay, so far so good. Next, what we can do is we recall from our previous video that in order for our generalized estimator to be unbiased, the sum of the weights had to equal 1, right? So now what we're going to do is we're going to take account of the condition for unbiasedness. So the condition for unbiasedness was that lambda 1 plus lambda 2 should equal 1, right? The sum of these weights should have equaled 1. So was the condition for unbiasedness. So taking account of this condition, what we're going to do is we can rewrite the variance of Z by substituting for lambda 2. Okay, so this can be rewritten as follows. So this becomes sigma squared x times lambda 1 squared. So lambda 2 is simply 1 minus lambda 1, right? That's what we get if we rearrange this expression on the right hand side. So lambda 2 becomes 1 minus lambda 1. So this can be rewritten as 1 minus lambda 1, the whole thing squared. So this is what we have. Okay. Next, what we can do is we can expand this quadratic, that is 1 minus lambda 1 whole squared. We can expand that. And when we do that, this is what we get. So sigma squared x times, so we have lambda 1 squared, and when we expand this quadratic we get plus 1 minus 2 times lambda 1 plus lambda 1 squared, and this simply equals sigma squared x times lambda 1, sorry, this is going to be 2 times lambda 1. Let me just erase that. In fact, it's a good idea to continue in on the next line. So this becomes, when we simplify it, it becomes sigma squared x times, so this is going to be added, right? So we get lambda 1 squared, but this is going to be 2 times lambda 1 squared plus 1 minus 2 times lambda 1. Okay, so this is what we get. And what we can do next is that in order to minimize the variance of z, we need to choose lambda 1 such that the variance of z is minimized, right? So in order to minimize this, we're going to differentiate this because that's what we do. We take the derivative. So that's what we're going to do next. So let me just write down what we're doing to minimize variance of z. We must choose lambda 1 so as to minimize the expression. So this is the expression that we are going to work with. This is the expression that we are going to work with. And let's continue on the next slide. Okay, cool. So let me just rewrite the expression first. So we had the variance of sigma squared z is equal to sigma squared x times 2 times lambda 1 squared minus 2 times lambda 1 plus 1. This is what we had. And we are going to now differentiate this with respect to lambda 1 to obtain the first order condition. So to obtain the first order condition, we differentiate with respect to lambda 1. Differentiate with respect to lambda 1. So when we do that, this is what we're basically doing. We're differentiating with respect to lambda 1 and we equate to 0. So when we do that, we can see that this simply equals 4 times lambda 1 minus 2. And when we equate this to 0, we can simplify this to find that lambda 1 is going to equal 0.5, okay, because 2 is going to go to the other side. So we get 4 times lambda 1 equal to 2, right? And then lambda 1 is simply equal to 2 over 4, which is 1 over 2, which is just 0.5. So we find that lambda 1 is equal to 0.5 is when the variance is minimized, and we can also confirm that this is indeed a minimum by taking the second derivative. So when we differentiate this, so let me do that. So if we take the second derivative, we find that the second derivative is positive. So that confirms that we have a minimum. Right. And this is just an extra step. You may not have to do this in your exam, but it's a good idea to always check that you have a minimum. So next, we can conclude that the expression is minimized for lambda 1 is equal to 0.5. This is where that expression is minimized. This expression is minimized when lambda 1 is equal to 0.5. Now, what we were trying to do is that we were trying to find the condition where the variance is minimized, right? And we have found that we already remember from our initial condition for unbiasedness that lambda 1 plus lambda 2 must equal 1, right? Therefore, lambda 1 is equal to lambda 2 is equal to 0.5. So we have demonstrated that the sample mean is indeed the most efficient unbiased estimator, at least in the example that we have just discussed in this video as well as the previous one.